Imagine this. You're looking at the night sky, and for a brief moment, it feels like the stars are looking back. Sounds like science fiction, right? But what if first told you that there are objects in space that seem to react to our observation, as if they are where we are watching? It's a mind-bending concept that's been puzzling scientists and stargazers alike. In this video, we are diving into the mysterious world of quantum physics and exploring phenomena that challenge our understanding of reality. You won't want to miss this. It's a journey that might just change the way you see the universe. The phenomenon of objects behaving differently when observed is a fascinating and somewhat perplexing aspect of quantum physics. It's a topic that has intrigued scientists and laypeople alike. At the heart of this phenomenon is the observer effect, a principle that suggests the act of observation can influence the behavior of particles at the quantum level. This isn't just a theoretical concept, it's been demonstrated in various experiments. One of the earliest recorded instances of this effect comes from the famous double-slit experiment. In this experiment, particles like electrons or photons are fired at a barrier with two slits. When unobserved, these particles create an interference pattern, behaving like waves. However, when observed, they act like particles and create a different pattern. This suggests that the act of observation somehow changes the behavior of these tiny particles. It's as if they are aware they're being watched and change their behavior accordingly. Another example is the quantum Zeno effect. This is a phenomenon where a quantum system can be prevented from changing if it is observed frequently enough. Imagine a spinning coin. If you keep looking at it, it seems to stay in its current state longer than it would if you left it alone. This effect has been observed in various quantum systems, further supporting the idea that observation can influence behavior. It's a bit like having a superpower, where just by looking at something, you can change how it behaves. Some objects in space exhibit peculiar behaviors when observed, particularly changes in movement and brightness that seem to coincide with human monitoring. This phenomenon, often referred to as the observer effect, has been noted in various astronomical observations. One of the most famous examples is the behavior of certain asteroids. When astronomers closely monitor these space rocks, they sometimes observe sudden changes in their brightness or even their trajectories. This could be due to the subtle forces exerted by the observation process itself, such as the pressure from light used to observe them, which can slightly alter their paths. Another intriguing case involves variable stars, which naturally fluctuate in brightness. However, some of these stars exhibit unusual patterns that seem to correlate with periods of intense human observation. For instance, certain stars might show unexpected dips or spikes in brightness when astronomers are actively studying them. This could be attributed to the increased data collection and analysis, which might reveal previously unnoticed variations. It's a bit like how a plant might grow better when someone pays more attention to it, but on a cosmic scale. The phenomenon isn't limited to natural objects. Artificial satellites and space probes have also shown changes in behavior when under scrutiny. For example, some satellites have exhibited unexpected shifts in their orbits or communication patterns when ground stations are actively tracking them. This could be due to the slight thermal or electromagnetic effects caused by the observation equipment. It's a reminder that even in the vastness of space, human interaction can have measurable effects. These observations raise interesting questions about the nature of observation itself. Is it possible that our methods of studying the cosmos are influencing the very objects we are trying to understand? While it's a fascinating topic, it's important to note that these effects are usually minimal and don't significantly alter our understanding of the universe. They do, however, highlight the delicate balance between observer and observed, even in the realm of astronomy. Over the years, astronomers have noticed something peculiar. Certain objects in space seem to behave differently when observed. This isn't just a one-off occurrence. It happened repeatedly, across decades, and recorded by different missions. The most famous example is the WOW signal. It was a strong narrowband radio signal received on August 15, 1977, by Ohio State University's Big Ear radio telescope in the United States. It lasted for 72 seconds and was so named by astronomer Jerry R. Emmon, who circled on the printout and wrote "WOW" in the margin. Despite extensive searches, the signal has never been detected again. Another intriguing case involves pulsars. These are rotating neutron stars that emit regular pulses of radiation. In the late 1960s, astronomer Jocelyn Bell Burnell and her team discovered the first pulsar. They initially considered the possibility that the signals were artificial, perhaps even from an extraterrestrial intelligence. However, further observations revealed that pulsars are natural phenomena. Yet, There have been instances where pulsars have exhibited unusual behavior. For example, some pulsars have been known to glitch, suddenly speeding up their rotation rate. This is thought to be due to a sudden redistribution of mass within the neutron star. The phenomenon of objects in space reacting to observation isn't limited to radio signals and pulsars. In the 1990s, astronomers noticed something odd about the comet Hale-Bopp. Despite being a long-period comet, it exhibited unusual activity even when it was far from the Sun. Some scientists speculated that this could be due to the comet being observed more intensely than others. However, this is still a topic of debate. What's clear is that the behavior of objects in space can be complex and sometimes unpredictable. It's a reminder that there's still much we don't understand about the universe. Measurement tools are not passive observers. They actively participate in the phenomena they measure. This is especially true in the realm of quantum mechanics, where the act of observation can influence the outcome. Instruments used to detect and measure objects in space, such as telescopes and particle detectors, are not perfect. They have their own imperfections, limitations, and even introduce their own noise into the data. For instance, the Hubble Space Telescope, despite its impressive capabilities, has a known issue called charge transfer inefficiency. This means that as electrons move across the detector, some get stuck, creating a kind of blurring in the images. This isn't a flaw in the universe, it's a flaw in our measurement tool. Moreover, the very act of measuring can disturb the system being observed. In quantum mechanics, this is known as the observer effect. For example, when measuring the position of an electron, the photons used to observe it can change the electron's momentum. This isn't just a theoretical concept, it's been demonstrated in experiments. It's like trying to measure the temperature of a cup of coffee with a thermometer that's also heating up the coffee. The tool isn't just observing, it's interacting. In astronomy, this interaction can be more subtle but is still present. For instance, when we use radio telescopes to observe distant objects, the telescopes themselves emit some radio noise. This noise can interfere with the signals they're trying to detect. To mitigate this, scientists use sophisticated techniques to filter out the noise. But it's a constant challenge. It's like trying to listen to a whisper in a crowded room. You have to tune out all the other sounds to hear it clearly. Furthermore, the resolution and sensitivity of our instruments limit what we can observe. For example, the Event Horizon Telescope, which captured the first image of a black hole, has a finite resolution. This means that some details, smaller than the telescope's resolution limit, are simply invisible to it. It's like trying to read the fine print on a document with a magnifying glass that's not powerful enough. You can see the general shape of the letters, but the details are lost. This isn't a limitation of the universe, it's a limitation of our tools. As our tools improve, so does our understanding of the cosmos. But it's crucial to remember that our tools are not perfect, and they shape the data we collect. In the realm of quantum physics, there's a peculiar phenomenon that has left scientists scratching their heads. It's called the observer effect, and it's a situation where the act of observing a particle changes its behavior. This isn't just a quirk, it's a fundamental part of quantum mechanics. The problem is, traditional physics struggles to fully explain why this happens. Think of it like this. In everyday life, if you watch a ball roll down a hill, your observation doesn't change its path. But in the quantum world, things don't work that way. When you measure a quantum particle, you force it to choose a state. It's like asking a spinning coin to decide if it's heads or tails before it lands. This is a big deal because it challenges our classical understanding of cause and effect. Here's where things get even more interesting. There's a thought experiment called Schrödinger's cat that illustrates this point. Imagine a cat in a box with a device that has a 50% of chance of releasing poison. Until you open the box, the cat is both alive and dead at the same time. It's only when you observe it that the cat chooses a state. This might seem like a silly example, but it highlights a real issue in physics. Traditional physics can't explain why observation affects the outcome. Some scientists have tried to explain this using a concept called decoherence. The idea is that the act of measuring a particle causes it to interact with its environment, which in turn forces it to choose a state. But even this explanation isn't perfect. It doesn't fully account for why observation seems to have such a dramatic effect. It's a puzzle that continues to challenge our understanding of the universe. The idea that objects in space might react to human observation is a fascinating one, and it draws some intriguing parallels with the world of quantum mechanics. In the quantum realm, particles can exist in multiple states at once, a property known as superposition. It's only when we observe or measure these particles that they choose a definite state. This is often referred to as the observer effect. Similarly, some theories in cosmology suggest that large-scale structures in the universe might exhibit behavior that seems to respond to observation, although this is a highly debated and speculative area. One of the most striking parallels is the concept of wave function collapse in quantum mechanics. When a quantum system is observed, its wave function collapses from a superposition of states into a single, definite state. Some cosmological models propose that the universe might undergo a similar kind of collapse or change when observed. For example, the idea of a participatory universe suggests that consciousness plays a role in shaping reality. While this is a controversial idea, it does draw a fascinating parallel with quantum behavior. Another interesting comparison is the role of probability in both quantum mechanics and cosmology. In quantum mechanics, the behavior of particles is described by probabilities rather than certainties. Similarly, in cosmology, the behavior of large-scale structures is often described in terms of probabilities and statistical distributions. This probabilistic nature is a common thread that runs through both the very small and the very large scales of the universe. Moreover, the concept of entanglement in quantum mechanics has its own cosmic scale counterpart. Quantum entanglement occurs when particles become linked and the state of one particle instantly affects the state of the other, no matter the distance between them. Some theories in cosmology suggest that the universe might have a similar kind of interconnectedness, where changes in one part of the universe could instantaneously affect another part. This idea, known as non-locality, is a key feature of both quantum mechanics and certain cosmological models. Scientists often tread carefully when discussing phenomena that seem to react to human observation, like the famous observer effect in quantum physics. This caution stems from a deep-seated fear of misinterpretation and the potential ridicule that can follow. The scientific community values evidence-based conclusions, and topics that venture into the realm of consciousness influencing physical reality can be contentious. Missteps in communication can lead to sensationalism, which overshadows the nuanced and often preliminary nature of the research. Public discourse on such topics can quickly spiral into misunderstandings. For instance, the idea that simply observing a quantum particle changes its behavior is a well-documented phenomenon. However, extending this concept to larger, more complex systems, like objects in space, can be met with skepticism. Scientists worry that the public might misinterpret these discussions as endorsing pseudoscience or paranormal claims. This fear is not unfounded, as history has shown that sensationalized reports can lead to a loss of credibility for both the researchers and the scientific community as a whole. Moreover, the peer review process, which is the backbone of scientific validation, can be slow and meticulous. Researchers often prefer to wait until their findings are robust and widely accepted within their field before engaging in public discussions. This cautious approach helps to avoid premature conclusions and the subsequent backlash that can arise from misinterpreted data. For example, studies on the potential influence of human consciousness on physical systems are still in their infancy. Sharing these findings prematurely could lead to misinformation and undue pressure on researchers to provide definitive answers before the science is fully understood. Another factor is the potential for ridicule from colleagues. The scientific community can be highly critical, and venturing into areas that are not yet mainstream can be career-limiting. Scientists often prioritize their professional reputation and the respect of their peers. Public discussions on controversial topics can attract unwanted scrutiny and skepticism, which can hinder future research opportunities. This is why many researchers choose to focus on more accepted areas of study, even if they are personally intrigued by the mysteries of human observation and its potential effects on the physical world. The idea that observation can influence the behavior of objects in space might sound like science fiction, but it's a concept that has been explored in both quantum physics and philosophy. At the quantum level, particles don't have definite states until they are measured. This is known as the observer effect. It's not that a human observer is necessary. Any interaction that causes a measurement can affect the outcome. For instance, when you try to measure the position of an electron, the act of measurement itself can change the electron's momentum. This isn't just a theoretical quirk, it's a fundamental aspect of quantum mechanics. It suggests that the universe at its smaller scales is probabilistic, and that observation collapses these probabilities into definite states. This concept can be unsettling. It implies that the act of looking at something can change it. In the macroscopic world, this doesn't seem to happen. A tree falling in a forest makes a sound whether or not someone is there to hear it. But in the quantum world, things are different. It's as if the universe is waiting for us to look before it decides what to be. This isn't just a philosophical musing, it's a practical reality in quantum experiments. Scientists have to account for the observer effect when designing experiments. They use clever techniques to minimize the impact of measurement, but it's always there, lurking in the background. The implications of this are profound. If observation can influence the behavior of particles, does that mean consciousness plays a role in shaping reality? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that consciousness is necessary to collapse the wave function. Others, like the many worlds interpretation, avoid this conclusion by suggesting that all possible outcomes actually happen in separate branches of the universe. But even if consciousness isn't necessary, the idea that observation can change things is still disturbing. It suggests that the universe is not a passive place, but an active one, where our interactions with it can change its behavior. This isn't just an abstract idea. It has real-world implications. In quantum computing, for example, the observer effect is a major challenge. Quantum bits, or qubits, are incredibly sensitive to measurement. Any interaction with them can cause them to lose their quantum state, a process known as decoherence. This makes designing quantum computers incredibly difficult. Scientists have to find ways to manipulate qubits without measuring them directly. It's a delicate balancing act, and one that highlights the very real impact of the observer effect. So, while the idea that observation can influence the behavior of objects in space might seem like science fiction, it's a very real and very disturbing aspect of our universe. Alright, let's wrap this up. So, we've explored some mind-bending stuff today. We've seen how objects in space, like the double-slit experiment and quantum particles, seem to behave differently when we observe them. It's like they're playing a cosmic game of peekaboo, changing their behavior just because we are watching. Isn't that wild? It's as if the universe is saying, hey, first know you're looking, and first am going to change just to mess with you. Now, first know this stuff can be a lot to take in. It's like trying to understand a magic trick, but the magician is the universe itself. But that's the beauty of it, isn't it? The universe is full of mysteries, and these quantum witnesses are just a few of them. They remind us that there's so much we don't know, and that's what makes science so exciting. So, what's next? Well, if you're as fascinated by this as first am, stay tuned. We've got more mind-blowing topics coming your way. Maybe we'll dive into the mysteries of dark matter, or perhaps we'll explore the weirdness of black holes. Who knows? The universe is vast, and there's always more to discover. But for now, first want to hear from you. Did any of these quantum witnesses blow your mind? Do you have any theories of your own? Share your thoughts in the comments below. Let's keep the conversation going and explore the mysteries of the universe together. And remember, the next time you look up at the night sky, think about those little particles playing hide and seek. The universe is weirder and more wonderful than we can imagine. See you in the next video.